Welcome to Episode 28, Configuration Management, Part 4, Advanced Topics and Metrics. As programs mature, configuration management becomes more than a safety net. It becomes a competitive advantage. Mature teams treat change as a continuous flow, supported by automation, evidence, and measurement. The focus shifts from simply preventing failure to understanding why things succeed. Capability growth often starts with codified processes, but evolves into data-driven improvement. The question moves from, did we follow the policy, to how can we make this safer, faster, and more predictable? This mindset defines a modern, mature configuration management capability built on advanced techniques and meaningful metrics. Building on that, immutable infrastructure and ephemeral instances redefine how environments are maintained. In an immutable model, systems are never modified in place. Instead, new instances are built from clean templates and deployed to replace the old. When issues arise, the instance is destroyed rather than repaired. This approach eliminates configuration drift and ensures that every deployment begins from a known state. Picture a web server image rebuilt for each release rather than patched repeatedly over months. Such disposability may seem wasteful, but delivers stability and consistency at scale. Ephemeral infrastructure makes rollback as simple as redeployment, drastically reducing human error and maintenance debt. From there, declarative enforcement with automatic reconciliation ensures systems remain aligned to their defined state. Declarative tools describe what the environment should look like, not how to reach it. The system itself performs reconciliation, correcting drift whenever it appears. Imagine defining a network policy that always limits administrative access to specific subnets. If someone changes that rule manually, the declarative engine restores it automatically. This form of self-healing creates confidence that configurations cannot quietly diverge. Declarative enforcement represents a shift from manual verification to continuous correction, where compliance becomes an ongoing property, not a periodic event. Extending trust further, signed artifacts and attested provenance secure the software supply chain from development through deployment. Each build artifact, whether a binary, container image, or script, is digitally signed to confirm its origin and integrity. Provenance data adds context, such as build environment, dependencies, and responsible teams. For example, a container image might carry metadata proving it was built from a specific repository by a verified process. When deployed, the system validates the signature before accepting it. This assurance prevents tampering and ensures that what reaches production is exactly what passed review. Signed provenance connects accountability directly to code, transforming transparency into a measurable control. Building on that idea, integrating software bills of materials into configuration management provides a complete inventory of software components. A software bill of materials, often called an SBOM, lists every library and dependency in a system. Integrating it with configuration data allows automatic correlation between environment versions and component vulnerabilities. Suppose a new vulnerability appears in a popular cryptographic library. A connected SBOM instantly shows which systems use that version and where remediation is required. This integration turns what was once detective work into a rapid, targeted response. Over time, it becomes a cornerstone of both security assurance and efficient maintenance. Moving deeper, kernel, module, and firmware governance extend configuration discipline to the hardware and operating system layers often overlooked. Kernels and firmware define the base trust on which all higher configurations rest. Allowing unverified or outdated firmware undermines every control above it. Establishing signed updates, verified drivers, and attested boot sequences ensures full stack integrity. For instance, a data center may require cryptographically signed firmware before devices are admitted to production networks. Monitoring versions and patch levels prevents exposure from outdated modules. Strong governance at this level reinforces the security foundation that all configuration management depends on. Before major updates, blast radius analysis helps teams understand potential impact and containment strategies. The blast radius represents how far a change could spread if something goes wrong. Analyzing it forces teams to define dependencies, fault domains, and rollback boundaries. For example, updating a shared library used by multiple services should be staged carefully so an error in one does not cascade across all. Visualizing the blast radius clarifies who must be notified and what contingency plans are needed. This analysis turns abstract risk into an actionable design element, allowing safer scaling of change. Building resilience further, chaos drills validate that rollback and recovery mechanisms work as intended. Chaos drills deliberately simulate failures or misconfigurations to test detection and response. Imagine disabling a configuration parameter in a staging environment to confirm whether automated rollback occurs within minutes. These exercises transform assumptions about recovery into measurable performance data. The key is to conduct them safely, with scope controls and monitoring in place. By rehearsing failure deliberately, organizations build reflexes that serve them during real incidents. Chaos drills prove that resilience is not theoretical, but operationally verified. From there, segmented rollout strategies across tenants or environments minimize shared risk and improve learning. Instead of pushing a configuration change to all systems simultaneously, teams can deploy in logical groups or tenants. Each segment serves as a validation layer before expanding further. Consider a software platform serving multiple clients. Releasing configuration updates to one tenant first reveals unexpected interactions before global rollout. Segmented strategies balance speed and safety by coupling deployment with observation. This structured approach transforms deployment into a feedback-driven experiment that scales confidently. Continuing that momentum, automated drift identification and correction systems provide constant oversight. Drift occurs when real-world configurations diverge from defined baselines due to manual intervention, failed automation, or external factors. Automated detection compares live states against stored definitions and repairs discrepancies immediately or through scheduled updates. For example, a monitoring system might notice that an encryption setting has reverted to default and automatically apply the approved configuration. Such feedback loops close gaps before they cause incidents. They also feed valuable trend data into compliance dashboards, proving control effectiveness in near real time. To measure maturity, tracking change failure rate trends gives direct insight into process stability. Change failure rate represents the percentage of changes that result in incidents, rollbacks, or degraded service. When this number decreases, it signals that planning, testing, and approvals are working. When it rises, root causes must be explored. A sustained reduction in failures often follows improvements in peer reviews or automated testing coverage. Tracking these patterns across teams provides objective feedback on whether configuration management practices are improving. Over time, change failure rate becomes a vital performance indicator linking discipline to outcome. Complementing that measure, metrics such as lead time and recovery duration show how quickly organizations can adapt and respond. Lead time measures how long it takes a change to move from proposal to successful deployment. Mean time to recovery tracks how fast the system returns to a stable state after a failed change. Together, they reveal agility without compromising reliability. For instance, reducing lead time while keeping failure rates low demonstrates genuine maturity, not recklessness. These metrics shift discussions from anecdotal claims to quantitative analysis. They make continuous improvement visible, measurable, and motivating. Finally, audit readiness without slowing delivery reflects the balance every modern organization seeks. Continuous evidence collection, automated approvals, and well-structured records mean audits become verification exercises rather than disruptions. When every change already carries linked tickets, logs, and signatures, audit response time shrinks dramatically. Teams no longer scramble to reconstruct history because the proof is built in. Achieving this state requires careful design but yields immense efficiency. Audit readiness, once seen as overhead, becomes a natural outcome of disciplined automation and transparency. It closes the loop between compliance, velocity, and trust. In closing, advanced and measurable configuration discipline turns change management into a self-improving system. Immutable builds, declarative control, provenance tracking, and meaningful metrics together create transparency and precision. Teams gain confidence that every change is traceable, recoverable, and aligned with purpose. Measurement ensures progress is visible, while automation ensures consistency. As organizations evolve, configuration management becomes the quiet engine of stability beneath constant change. By mastering both practice and proof, they reach a point where improvement itself is systematic and sustainable. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.